Hello, everybody. My name is Bhatia,
And I'm David Rodriguez.
and together we are two seniors from Cerritos High School, and we have captained this mission. So first and foremost, we would like to thank the companies, organizations, and corporations whose publications provided the data and research necessary for this mission.
So to start this mission, we took the competition prompt and turned it into a design brief. The reason for this was because in our engineering classes, that's how we start. So we formulated this design brief to meet all of our objectives for this mission. So our design brief is to design a two-person Mars flyby mission that can be launched no later than 2024, that is as cost-effective, safe, and simple as possible.
So with that, we bring our key ideals in mind. The first one, of course, being safety. And with safety, we do not only refer to astronaut health, but also the vehicles we use must have the adequate radiation protection, and the trajectory used must be safe enough for the astronauts. Next up, we have simplicity. Simplicity in the sense that if we're using two different branded vehicles for space, we need to make sure that they're compatible. And in the course of the trajectory, it needs to be simple enough that we can actually achieve it with the vehicles we're using. And lastly, feasibility. It has to make sorry about that. It has to make sense. We can't just stack everything up on one SLS and launch it to space and say we got to Mars. It has to make practical sense. So with that, we bring you our trajectory.
So we're presenting our trajectory first to give you a basic outline of our mission. So as you can see here, the blue circle is Earth's orbit and the red circle is Mars' orbit. The green circle is our space vehicle, our spacecraft's path. It is quite a long orbit, as you can see, and it is approximately 1.97 years.
So although the orbit is a duration of approximately 2 years, the plus side to that is our total delta V is only 4.31 kilometers per second, which means that we can optimize the mass we want to move across space with the minimum amount of fuel. So our first idea we would like to present to you today is Frankenstein, and it's from Mary Shelley's famous book, Frankenstein. What we have is a Dragon V2 capsule placed on top of 3 Dragon trunks assembled to form one habitat unit. As you can see, we have taken what we have, pieced it together to create our own contraption. Now, initially, in low Earth orbit, once the solar arrays are deployed, we see that the Dragon capsule's heat shield prohibits access to this habitat module. But after a simple 180-degree maneuver and docking into the habitat module, the astronauts have access.
Our second idea was Braun 12. Braun named after Werner von Braun, the father of rocket science, and 12 for the number of team members that we have. So this is composed of 3 vehicles. On the left is the Dragon V2 with its trunk. In the center is the Bigelow B330 habitat module. And on the right is the Falcon Heavy, which will be used for thrust.
So when we compare these two ideas side by side, the Frankenstein mission can be achieved in one launch as the mass allows it to do so and the Falcon Heavy's capabilities, but it is a major modification. We're taking not only 1 unpressurized trunk, but 3, and assembling them together to form one pressurized habitat unit. And it also presents a limited and compact design.
For Braun 12, there's 2 launches, one of the Falcon Heavy and one of a Falcon 9 to transport our B330 and Dragon V2 spacecrafts into low Earth orbit. A positive is that the B330 is a massive habitat for the astronauts to have, and it is technologically on track. All of these vehicles will be ready to be launched for our time frame.
So in line with the engineering process, we really made our decision using the decision matrix. The design criteria goes as follows: feasibility, cost, safety, simplicity, and any technical modification necessary. what I would really like to point out here when we compare the two is the safety and technical modification needed for the Frankenstein mission. It earned scores of 6 and 5 due to the limited and compact design that only provided 45 cubic meters, and the supplies alone are 42. But the Braun 12 earned a 10 in safety relative to the Frankenstein, as it not only provides adequate room inside, but its shell also provides a safety from radiation, cosmic radiation, solar, and EMPs.
So a quick mission overview. The two rockets that we will be using will be from SpaceX, the Falcon Heavy and the Falcon 9. The crew vehicle will be the Dragon V2, which is what we will use to get them into space, and the habitat module is the Bigelow B330.
So the first half of the mission schedule. Day 0 for us actually begins once the Dragon V2 capsule has docked and confirmed its safety with the Bigelow B330. And after that, the first week is really spent with the crew members making sure that all systems, technology, and everything is working with mission control back and forth. And then we hit our first big block of approximately 1.12 years, where the astronauts trans-Mars inject from the low Earth orbit to the flight path we had shown. And lastly, from days 595 to 607, the astronauts prepare vigorously by setting up scientific equipment and cameras to record the flyby.
So the second part of our mission schedule. Our Mars flyby will be October 28th, 2022, at a speed of 11.67 kilometers per second and at an altitude of 77,300 kilometers. Again, after the flyby, there will be a block of time of approximately 100 days where the astronauts will be traveling back to Earth. And a week before they re-enter Earth's atmosphere, they will begin to get the spacecraft ready and do any technical checks to make sure that they will be ready to enter. And on day 720, on February 17th, 2023, the astronauts will re-enter Earth's atmosphere and come home. So prior to launch, SpaceX is headquartered in Hawthorne, California, and we are using 3 SpaceX vehicles. So to get our vehicles from Hawthorne, California to Kennedy Space Center in Florida, which is our launch site, we would have to use a procession of approximately 50 trucks overland to Florida. While this may seem extreme, this is SpaceX's current transportation procedure to get their rockets to Kennedy Space Center. The Bigelow B330, produced by Bigelow Aerospace, is located in Las Vegas. So it too will have to be trucked from Las Vegas to Florida. And once the cargo gets to Kennedy Space Center, they will be diverted, as there are 2 launches. The Falcon Heavy and the B330 will be diverted to Launch Complex 39A, and the Falcon 9 and Dragon V2 will be diverted to Launch Complex 40.
So with that, we begin with departure. Our first launch consists of the Falcon Heavy carrying the Bigelow B330 in a modified fairing to provide for the excessive diameter of the B330. It is delivered to low Earth orbit, and systems checks are run from mission control to make sure all computers on board are functioning, and as well as other technologies. In a matter of 3 days later, three days later, we launched the astronauts in the Dragon V2 capsule on the Falcon Heavy into the same orbit, where they will assemble with the B330 on February 24th, 2021. Now, a cool feature about this is that the astronauts can manually dock. However, SpaceX does provide a feature on board the spacecraft where mission control can actually control the Dragon V2 and its docking procedure.
So on February 27, 2021, this is when we shoot off to Mars for the trans-Mars injection. So the Falcon Heavy burns for 4.27 kilometers for a delta V of 4.27 kilometers per second to head off to Mars. And once the Falcon Heavy burn is complete, through the use of explosive bolts, the Bigelow B330 and Dragon V2 will detach itself from the rocket and be on its way to Mars.
Here we have an accurate visual depiction of what the Braun 12 spacecraft will actually look like on its way to Mars. As you can see, in the lead is the Bigelow B330 module, followed by the Dragon V2. And upon flyby on October 28, 2022, the Braun 12 spacecraft flies by Mars at a velocity of 11.67 kilometers per second and an altitude, as mentioned before, of 77,300 kilometers. Now, what's actually interesting about this altitude is that it's the sweet spot to take gravity assist to our advantage. The delta V here is a change of only 42 meters per second. But if we can hit this altitude, we will not need to burn any fuel in the process.
So February 17th, 2023 is when we will re-enter Earth's atmosphere. So on the way there, the B330 and the Dragon V2 will separate, and the B330 will go into highly elliptical Earth orbit for later use. The Dragon V2 will detach from its trunk. The trunk will deteriorate in the Earth's atmosphere. The Dragon V2 will encounter the Earth's atmosphere, and it will cause aerobraking, which will slow it down. And once it has reached adequate speed, parachutes will deploy and safely drop the Dragon V2 into a nearby ship in the Atlantic. So, like we had mentioned before, our mission is 720 days, and that provides a lot of downtime for the astronauts. So we try to give them as much of an Earth routine as possible, with a few key aspects. One being video log. They have to video log their journey for proper documentation, as well as we will give them time to do scientific experiments and research and exercise. They will have to exercise frequently to counter the physical effects of being in a prolonged time in space with no gravity.
So now, what are the more important questions? What about the food? Well, we're following NASA's guideline of 1.7 kilograms per astronaut per day, and we will be following calorie intakes from the National Research Council, which also will include vitamins to reduce bone density loss. And our total for food comes down to, in terms of mass, 2,465 kilograms, approximately $12 million worth. So you could quite say that our astronauts may gain weight when they re-enter Earth. And during their downtime, we do have scientific experimentation, which includes botanical cultivation, study of human psychology in deep space environments, telescopic research with the human eye, and study of biological effects on human health. But this mission will only be a success if we can get the community involved. And with that, we've included Q&A sessions with media where locals can just ask questions to the astronauts up there. And experiments designed by students all the way from elementary school to university level can have their simple experiments conducted up in space. We will be re-inspiring we will be doing what the Apollo program did for all of us. Inspire us to go out into space once again. And that is exactly what we plan to do. Push the envelope of engineering and the aerospace industry.
So the astronauts need an environment for all that downtime and to conduct their activities. So this will be essentially the astronauts' house, so that it has everything that they need to live. Towards the front of the B330 will be personal quarters. This is where they will sleep. They will have their own personal effects and where they will spend their own personal time. Towards the rear of the B330 is the bridge, where they will be able to be in contact with mission control as well as see all the technical data about their spacecraft. The center is where the fitness equipment, galley, and storage will be. Towards the front is the commons area, which is where they will eat and they can perform any recreational activities. And towards the rear is the personal hygiene equipment so that we can keep them as comfortable as possible during the trip.
So as we can see, the Bigelow B330 module provides everything astronauts need for a safe environment for this duration of 2 years. So although we do not have artificial gravity, we have all the life support systems necessary for astronauts to maintain their health. And with that, we give you our budget. So our budget is split into 3 parts. The first being vehicle and spacecraft cost. This includes the Falcon rockets, the Bigelow B330 module, and the Dragon V2. Next, we have the supplemental cost, which includes all computers, technologies, and other appliances on board the spacecraft, priced at approximately $114 million. And lastly, we have development and training. We have allocated $50 million per astronaut to make sure they receive the proper training from NASA at the Johnson Space Center in Texas, and an additional $250 million for an overall mission development leading up to the launch, which puts our grand total at approximately $900 million.
To conclude our presentation, we would like to end with a quote from President John F. Kennedy. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. With this statement, President Kennedy sent the moon as America's frontier, and we spent our resources and time, and we got ourselves there. So for our generation, Mars is our frontier, and we will get there. Thank you.
Thank you.
Well, again, my favorite question to the life support system. How will this work in the Bigelow habitat?
I'm sorry, can you please repeat the question?
The life support system, how will this work in the Bigelow? How will you support the crew in the Bigelow habitat?
Well, the Bigelow B330 is made to sustain astronauts in space. That's what it's created for, so it has the life support systems necessary on board.
Where is the ECLS? In the Dragon or also in the Bigelow?
So, well, regarding life support, everything will be conducted in the Bigelow B330. The Dragon is really just a transport vehicle for the astronauts to get up and connect with the Bigelow B330. But because of its 330 meters of cubic space, we have all equipment and an additional $100 million worth of whatever the astronauts need to make sure that they are healthy.
Okay, because I didn't see in the Bigelow design, I didn't see ECLS.
The mass of the spacecraft, that is the Dragon and the Bigelow and stuff that flies with it, and the mass and propellant on the stage that is pushing it into trans-Mars injection. What you're using, what kind of stage to push this into trans-Mars injection? How much mass is that? I'm just trying to get the numbers here.
So we don't really have the numbers, but what we initially had was that we were going to use the second stage of the Falcon Heavy to propel the spacecraft. However, that's not enough propellant and thrust. So instead of landing the booster stages, which can be done in principle, we will be using all leftover fuel, not land any Falcon rockets, and use it all to thrust the Braun 12 spacecraft for Mars.
Thank you. Okay, so any more questions here? Okay, thank you very much.